Today we have, I need to give you this theory because it depends on your work one, on your report. So I will explain today everything you need to know to complete report one. And this is a theory of nozzle flow, isentropic flow in the nozzle. We will see also non-isentropic flow in the nozzle, and then diffuser. I hope today we can finish this chapter in the book. Please, thank you for support. Please do not forget to ask questions in the comments or by voice. And I'm ready to answer your questions about the subject, because it will be our probably last class when we are talking about work one. So previously we had a differential equation explaining change of velocity with respect to change of area, equation which we received on our previous class. This is this equation on the left, on top. And this equation, as we may see from the book, can be solved analytically, integrating left and right side with respect to a reference area, A asterisk, and substituting velocity by Mach number. This is why instead of velocity, differential velocity, we have Mach number in this equation and gamma, adiabatic constant. This substitution done in purely analytical way, and if you are interested to see how this transformation of equation and solution is done, please follow book. Equation you see on the right top part of this screen is analytical solution, is an exact solution, let's say, and it relates to cross sections. Cross section with asterisk is a throat. I mark with the red color, garganta. And on this section, we always have a specific flow conditions, right? We have Mach 1 inside throat, and because of this, speed of flow or velocity of flow is equal to speed of sound, or vice versa. Okay, velocity is equal to speed of sound. This is why Mach is equal 1. This specific cross section is called characteristic cross section. This characteristic cross section, A asterisk, is utilized in solution of flow equation in the nozzle. This equation here on the right we call area Mach number relation. Okay, I will write down here area Mach relation. So if you see one day in the book something written about area Mach relation, this is exactly this equation you can see on the screen. What does it relate? It relates reference area, throat area, to any other arbitrary area in the nozzle. For example, A area in arbitrary cross section presented on figure 11. We must, when we analyze this equation, understand that such equation is a square equation, right? It has square in near Mach 2 here and here, so it can be considered a square equation. So it has two possible roots. These two roots are useful in solution of such equation. One root will correspond to subsonic flow. It will be giving us a root of Mach less than 1. And the second root will correspond to supersonic flow. It will give us an answer for Mach higher than 1. Okay. which are both possible for same value of area ratio. If I extend this nozzle to another side, okay, it's not so symmetric. I will try to make it more symmetric. We have Mach. Okay, probably another area, similar area to what we have on the other side. So this area is same as on the supersonic part, absolutely same area. So we have Mach smaller than 1 in this cross section, and in other cross section we have, for example, Mach bigger than 1. They both correspond to same area, and these are two solutions of area Mach number relation. Two solutions. So equation of flow in the nozzle is giving to us possibility to solve flow properties for accelerating flows in subsonic section and for decelerating flows in a supersonic section. Such equation is based on isentropic model. So flow is isentropic with the constant entropy, with constant stagnation pressure and constant stagnation temperature as well. And it simplifies a lot our life because we can use isentropic relations presented on chapter 8 and 9. And these equations can complement flow model of area Mach relation. So knowing Mach number, using isentropic relation and considering constant stagnation pressure and temperature, we can calculate all other thermodynamic and flow properties in our nozzle. This is a figure, very famous figure from Anderson, figure 1012. It is important because I suggest you in the task of report 1 to use such figure as a reference for your visualizations. Of course, we can combine inside one graphic several curves, right? But this way of showing results is very useful. We have equation 1032, which is same Mach area relation or area Mach relation. And this area Mach relation, as you might see, gives us very important output, is that Mach number is only a function of area ratio between any arbitrary area and the area of throat. This area ratio is always bigger or equal than 1. Okay, cannot be some value smaller than 1 because area in smaller than throat cannot exist in the nozzle. If some area will be smaller than throat, this smaller area automatically becomes throat, so becomes a reference area. So in a nozzle, area smaller than throat area cannot exist and physically cannot exist as well. For example, if I have my, just as a small example, a nozzle like this throat, we have subsonic part, supersonic part. Okay, and then, for example, we have sudden decrease of area again, like this geometry. So this will become our throat. And in previous extreme minimal, this part where we had minimal area of flow is not a throat anymore. Here, Mach number will be different from Mach 1. It can be supersonic or subsonic, depending on many conditions. So that's it. Area is strictly related to Mach number, and Mach number does not depend on anything except the area ratio. also depends on gamma, but since gamma is constant for gas in a quite wide range of temperatures, we see that Mach number depends only on area. It does not depend on temperature, density, or pressure. It's just a function of area. So when we have this area function, as you can see on figure A, this one here, figure A, we can calculate this area ratio and solve area Mach number relation using equation 1032, obtain distribution of Mach number in a nozzle. How to check this solution, if it was correct or not? Once you solve, the left part before throat should be subsonic Mach number. Okay, this part should be subsonic Mach number, and the right part, let me choose another color, will be supersonic Mach number. So you should receive such a solution. Of course, as I told you, you have two roots of these equations. So for left part of the nozzle, you need to choose root which is Mach smaller than 1. Okay. And for the right part of the nozzle, you always choose another root which is Mach number more than 1. Exactly in the throat, where area is equal to reference area, you need to have Mach 1. So this is a checkpoint. Put 1 on the right side of this equation of area relation, and you will see that on the other side, on the right side of this equation, would be corresponding Mach number equal 1. So this is a checkpoint. If you receive different values in the throat, or you receive strange values in subsonic or supersonic part of the nozzle, usually you might have an error of programming of equation. Do not forget that this is a power here. So you need to put all this ratio of gamma plus 1 divided by gamma minus 1 in a power of big function. Okay. When you have this solution, picture B Mach distribution, then we use isentropic relations. For example, we see on part C, just I will make a bit smaller. On part C, we see a distribution of pressure. As a function of Mach number, there is only one parameter which enters in this equation, which is Mach number. So once you calculate Mach function, you can obtain this function here. And also temperature ratio. This function is absolutely same as we had in isentropic flow. So these are isentropic functions. Flow is isentropic. We can use these isentropic functions and plot these curves. Checkpoint for your calculation. There are several. On subsonic part of, I will remove these errors. They are useless, I think. On the subsonic part of the nozzle, we have a pressure ratio always bigger than 0.5. Okay, approximately 0.5 to 8 is a limit of pressure ratio. So you have relation between stagnation pressure and static pressure calculated. If you have something different in range in subsonic section, you can consider wrong calculation. And in supersonic section, we have pressure ratio always smaller than 0.5 to 8. This 0.5 to 8 you can receive if you put Mach 1 in isentropic relation, and you will obtain this value. I think we already had this limit of 0.5 to 8 in the previous discussion when we talked about characteristic point. Characteristic point is throat. Okay. So if you do not remember where this value of 0.5 to 8 came from, please go to definition of characteristic Mach number, M asterisk, and there was defined this limiting pressure ratio and temperature ratio for subsonic and supersonic flows. For temperatures, we know that the change is not so fast, not so abrupt, and it's approximately 83.3% ratio of temperature with respect to stagnation temperature. So in subsonic part of the nozzle, temperature stays almost constant and equal to stagnation temperature, and then in supersonic section it can significantly reduce. Significantly means several times with respect to initial stagnation pressure. Okay, so these values are different according to acceleration. More acceleration we have, bigger Mach number correspond to smaller pressure and correspond to smaller temperature inside the nozzle. And I would like to remind you that these parameters of pressure, I will correct here, pressure and the corresponding temperature and the corresponding Mach number, they all related one to another. So they are going all together in a package because area function influence on Mach function and Mach function influence on pressure and temperature. If you are interested to calculate density, you can also use density function for isentropic flow, which is similar to functions presented here, and they also included in Appendix A. And also, instead of isentropic function, you can use just equation of state, which is pressure is equal density multiplied by gas constant and multiplied by temperature. So once we have pressure and the temperature functions, we can get density functions from there and calculate just by this simple relation, not involving adiabatic constant, not involving power in function of density, and it becomes much simpler. Let me know if. Okay, thank you for your support for this situation which is happening. I hope Brazil also will show support to in a favor of peace, in favor of Ukraine, in favor of all other progressive countries which already shown their big support, and I hope everything will be better in future. Okay, I just remember that our class on last week, we finished with one question which I asked you. I would like to return for a few minutes to this question and ask again if someone of you discovered this paradox, which is same geometry of two different structures, same values in the inside of throat result in different type of flow. One flow is supersonic, another flow is subsonic. Please let me know if some of you discovered why different flows happen in same structure with same, let's say, boundary inlet conditions. Any ideas? Mauricio, tell me, do you have some idea?
Not really sure.
Okay. So then I probably need to explain, right? Same geometries on upper and lower picture, same flow model, same flow conditions in the throat, different results. One flow is supersonic, another is subsonic. We must understand what is a source of flow acceleration. Source of flow acceleration is always a pressure gradient. So the correct answer to my question is a pressure gradient. in the case of in case A, pressure gradient is accelerating flow, so pressure is decreasing. In case B, pressure gradient is opposite, pressure is increasing. This may happen in case A, when pressure ambient is much smaller than stagnation pressure, then flow is accelerating. And in case B, ambient pressure is similar or same to stagnation pressure, so flow is decelerating. Due to pressure gradient, this happens. So answer is what you have on the outside, on the exit, not on the entrance, what you have on the exit of this structure. This is why we might have same structure working in absolutely different way. Okay, accelerating to supersonic flow or not accelerating at all, or even decelerating flow, depending on pressure gradient between flow inside the nozzle and the outside on the exit. So this is the answer. Please do not forget, because this problem and this effect can be seen in many applications of nozzles and in real life, let's say. Okay, that was the answer. I hope it was clear. Next question. I would like to stop here to show you an example of calculation. Probably it would be interesting and important. I already showed this in my previous videos, so just one example, okay? And if you need more examples, more explanations, please visit questionnaire of gas dynamics, where I show how to solve examples, how to solve flow in the nozzles, different aspects of calculations. I think there are several examples in last videos of questionnaires when I show which tasks usually are asked on oral test, because on oral test you need to ask theoretical questions and need to show if you are capable to calculate analytically flow in the nozzle and other things. So let me show you just one example. I will assume my nozzle. I will, based on this picture we might see here, I will just remove few my notes, not to overload with informations, and I will write inside other calculations or some calculations. Okay, we will choose parameters on the entrance, and we will calculate parameters at any arbitrary point. I would like to have, okay, this entrance point, okay, this entrance, which I mark with the blue line, it will be my subsonic flow on the entrance. And for this cross section, okay, approximately, I will say that it's approximately 3 times bigger than throat. So this section 1 would be A1 divided by A asterisk relative area is 3. Okay, and let me calculate in same section, but in supersonic part. Okay, this also will be same area. This is section 2. On this section, I will have A2 by A asterisk is also equal 3. Just for simplicity, we can choose another value. It's absolutely not important which value we choose, because calculation is absolutely same method. And it's let's say it's simple, and the machine can always provide. Just put in the loop these operations. You can calculate for many points. So let's calculate Mach number. Let's calculate then pressure and temperature ratio. I can define that my pressure, stagnation pressure, is 10 atmosphere, for example, or 10 bar, not important. because we always use dimensionless ratios. And stagnation temperature, let it be 1000 Kelvin. This is important, okay? 1000 Kelvin. Temperature should be always used in Kelvin for such calculations. Please do not use centigrade or Celsius or Fahrenheit. It's wrong. These formulas are made for temperature in Kelvin. If you use other temperatures, you need to use correction from Kelvin to another units. But I hope you will not need it. So I define pressure, I define temperature, I define area ratio on entrance, I define area ratio in the middle, in supersonic section, and I would like to calculate starting from Mach number, okay? Because area will tell us what is Mach number at these 2 points. At point 0, Mach number is not equal 0, it will be some small value, and I will use isentropic relations, Appendix A. Inside Appendix A, we have, just to reminding you, we have Mach number. I write on the top right part of my screen. Mach number P0 by P, rho 0 by rho. We have T0 by T, temperature ratio, and we have A by A asterisk. This is a relation to nozzle relation. So I will look my nozzle ratio, area ratio, and I will search for a subsonic section. It's first part of table, and I will search for 3. Okay, where is it? It's somewhere in the first on the first page of. I will choose approximate value because it's not exactly equal 3. So I will see 3 on the subsonic section. I will see Mach number corresponds to 0.2 in the table. And the density I will not need, and pressure is 0.008. Pressure 1008. Sorry, 1008. So, it's temperature. So temperature 1008 and pressure 1028. 1028. I will not calculate density. There is no space for this number for density. And also, as I told you, you can calculate anytime, also by same equations or by equation of state. So I hope it's not a problem to calculate density when you know temperature and pressure. So these parameters we have for the subsonic part of flow. Okay, this is section 1, subsonic part. Mach 0.2, pressure close to stagnation pressure, temperature close to stagnation temperature. Pay attention that these values are always bigger than 1 because stagnation pressure and temperature and density are the highest values in the system. So you cannot receive this ratio smaller than 1. Okay. This ratio must be or equal 1, which corresponds to Mach 0 when flow is not moving. When flow is moving, this ratio will be always bigger than 1. And since we have, okay, I will put on graphics on part B is 0.2 point, is not exactly 0. 0.2. And then when I calculated 0.2, I will put on graphics of pressure should be reverse values. So somewhere here when this value is 1 divided by 1028, 1.028. This ratio here is because our graphics is reversed to Appendix A. Pay attention about this. These are reverse values. Okay, so you divide 1 by this value. I don't know why it happened, because it's traditionally like this. We plot functions between 0 and 1, right? But in Appendix A, it's functions always more than 1. So we need to calculate reverse values. And same for temperature. You see here in Appendix A is T0 divided by T, but in graphics is T divided by T0, also reverse value. Somewhere here would be 1 divided by 1008. Okay, so this is the value. Of course, it should correspond to our 0 coordinate, but it's not. Okay, I will forget that 1 is here. Actually, we can see, analyzing equation 1032, that if we would like to obtain Mach 0 from equation 1032, we need to have area ratio equal to infinity. So this right part should be infinite area to obtain Mach 0, which is physically impossible. Our nozzle is always finite. It has its dimensions. So Mach number inside nozzle cannot be equal 0. But we assume it very close to 0, right? 0.2 is incompressible. So from point of view of losses of energy is practically same as, not losses, sorry, ratio between pressures is practically same as for Mach 0. There is a question, could we use other absolute temperatures since we are working with ratios? No, we cannot. We cannot. Actually, we can if we make transformation. We just need to include in this formula also coefficient or transformation function. Then we can. Okay, but this formula is created in Kelvin because of convention of units, and because for calculation we are using dimensionless Mach number. So temperature ratio is also should be in corresponding units, and this is a ratio of Kelvin, not other temperatures. But we can calculate in other temperatures. Just apply to this function transformation, linear transformation, and you can use any units. But I think it complicates. Right, it's better to calculate in Kelvin, and then if you need to present after your result in other units like centigrade, you can do transformation of final result, not results inside calculation. But already the last step of calculation would be transformation to units you need. All calculations usually provide or dimensionless, without any dimension. For example, pressure ratio, temperature ratio are and Mach number, Reynolds number, they are dimensionless. So calculation can be dimensionless. And the last step is to transform to dimensional form. So I hope it's clear. By the way, Anderson in his book shows us calculation in other units. And he uses this transformation. You can see how to make it if you work for some company in the United States or others which require this transformation. It's absolutely not an issue to transform, but only after you calculate, because otherwise it makes difficult to understand your code by other people and can create some problems, because usually models are not simple, right? As much simple we have equations inside model, less chance that you have error inside model. Okay. All professional models which I saw in my life, or for engineering calculations, they work only with dimensionless models and dimensionless calculations. So all values are in range between 0 and 1, or Mach number is not so high as well. So all calculations in professional engineering world are dimensionless, and only the last step is conversion to dimensional form. I hope it's clear. Thank you for your question. So I calculate already subsonic part. Now I would like to calculate supersonic part. I will go to second half of Appendix A, which shows supersonic flow conditions, and I also will search for area ratio equal 3. There is no exactly area ratio 3, but there is an approximate value, closest value, which I will choose for this example. I found its area ratio 3.036, so it's 1% different from area ratio 3, almost nothing. And it corresponds to volume 2. Mach number 265. Then pressure ratio is 21.6, sorry, 21.6 pressure ratio, and temperature ratio 2.4. 2.4. It means that stagnation temperature is 2.4 times bigger than the static temperature, and stagnation pressure is 21.6 times bigger than static pressure. To put in this graphic, we need to reverse this function, to reverse this value. And I will put somewhere here, this point on figure B, Mach number 265. I hope you can see it on the figure B. I wrote 265, and then corresponding value of pressure ratio is 1 divided by 21.6. It's approximately 0.05. And corresponding value, just a moment, I will try to make a straight line. And the corresponding value of temperature ratio is 1 divided by 2.4. It's approximately 0.4. Yeah, approximately 0, more or less, 0.4. So we have dimensionless values. Once we are having these values, we can calculate dimensional values. Just need to multiply by reference our stagnation properties. To obtain pressure in dimensional form, we will need to multiply these ratios by 10, because our stagnation pressure is 10. And to obtain dimensional temperature, we need to multiply our dimensionless values by 1000, because our reference temperature, stagnation temperature, is equal 1000. I hope it's clear how to obtain dimensional from dimensionless. Please let me know if it was not clear, this part. Just one moment, I will take a glass of water and we can continue. Okay, I'm back. I do not see any questions, so I hope we can proceed. Next aspect is related to a problem. To a problem which I highlight in the first part of our lectures. What if we have not good pressure gradient? I mean, not good is pressure gradient which acts against the flow. We might see here a figure explaining such case. It's figure 1013. All these three pictures are correlated, so they are representing same case. Let's start from case 1 on part C, on view C of this figure. Case 1 represents pressure gradient very small, pressure to stagnation pressure ratio. I mean, very small means that change of pressure is small. PE1, case 1, it means pressure on the exit in case 1 is very close to initial pressure, P. Smaller, yes, it's smaller, but it's close. Why it's smaller, PE1 than P? Because otherwise flow will not go in direction we want, right? If we have PE1 bigger than P, then flow will go in different direction. So since we have flow in defined direction, which is shown on figure A, then we understand that PE1 is a bit smaller than P. Not so much. So what if we have a small pressure gradient? If we have a small pressure gradient, it means we have small energy for acceleration. Energy and acceleration are proportional to pressure gradient according to our flow equations, if you remember. They are correlated. So if we have small potential to accelerate, acceleration will be very small. It's also shown on graphics of Mach number, picture B, case 1. You see that flow in Mach number increases in the first part of the nozzle. But since energy of potential of this flow is small, not enough energy to accelerate even to sonic flow in the throat, it's subsonic. And in this case, unfortunately, in divergent part of the nozzle, flow decreases, decelerates again because flow remains subsonic. This is case 1. Case B or case 2 is very similar. PE in this case not approximately equal to pressure, but still smaller than pressure. It's okay, pressure gradient is bigger, but in case 2, still not sufficient for acceleration. Not sufficient for acceleration, not enough pressure for acceleration in throat. So flow becomes already compressible, Mach bigger than 0.3 at this point, okay, bigger than 0.3. But compressible flow does not mean that it will be supersonic. Compressible and supersonic are two different distinct definitions. One does not, the compressibility does not mean that it will become supersonic. If flow energy is not enough, if potential is not enough for acceleration, we cannot accelerate. Flow will still remain subsonic. Okay. And case 3 is an extreme case when flow has enough potential for acceleration. It corresponds to pressure. Okay, case 3, PE3 is approximately 2 times smaller than pressure Approximately. I say approximately because we need to reach this magic value of 0.528, or a bit more than 0.528. It depends on geometry of the nozzle, but approximately we can say that this value of PE3 is close to approximately 2 times smaller than inlet pressure. So if we have this magic value of PE3 close to half of inlet pressure, then inside throat we have sonic flow, Mach 1. This, as you can see from this graphic, is Mach 1. We reach Mach 1 at this moment. What will start to happen when our flow, for example, in case 4, PE4 would be smaller even. Okay, flow will still have more potential, because potential is the distance between inside the nozzle and exit of the nozzle. So if we have bigger potential, acceleration will be bigger and bigger and bigger. So this flow in the nozzle will start to be supersonic, partially then will decrease, something like this in case 4. In case 5, if we increase more, can be supersonic and then can decrease if potential is still not enough to sustain supersonic flow. And then there is some specific moment called PE6, where pressure is small enough to have a constant acceleration in all the nozzles. So pressure gradient is enough big to sustain a continuous acceleration flow in the nozzle. And this PE6 we already had right here. Just take a look on our previous example. In picture C, we have PE6 divided by P0. So pressure gradient is big enough to sustain supersonic acceleration, supersonic flow in divergent part of the nozzle and sustain continuous acceleration. So all is about pressure gradient. We need to see which is pressure gradient, which is pressure difference. Different cases can correspond to different flow pictures inside the nozzle. This case we had here in isentropic flow corresponds just to a case when energy is enough for continuous acceleration. If energy is not enough for continuous acceleration, we have figure like this here, which is divided in 2 distinct or different cases. Case 1 and 2 correspond to subsonic flow inside throat, and case 3, 4, 5, correspond to acceleration in a supersonic part and then deceleration. There is a question from Louise. Can the opposite also happen, where the flow starts and ends in a supersonic regime? Yes, flow is isentropic. This nozzle is isentropic. Model of flow is isentropic. So if we have a reverse flow, not in this direction, we have flow in an opposite direction, it can be going in absolutely same way. Flow enters supersonic, goes inside isentropic nozzle as supersonic flow, then compresses, reaches Mach 1 in throat, and goes out with subsonic conditions. But you already know what need to have to exit with the subsonic conditions to decelerate. You need to have significant pressure gradient that supports such flow. So you need to have reverse pressure gradient, and then such flow can happen. Since flow is isentropic, it's reversible. It can go in one direction or other direction. From computational point of view, we do not have any difference in which direction flow is going. For us, is important value of pressure and value of Mach number. If pressure gradient supports such as entropic flow, computationally it will be absolutely identical. So I hope I answer your question, and let me know if it's okay or you need more explanations if my answer was okay. Okay, thank you. Case choked flow is an important definition. Choked flow describes for us all flow cases when inside the throat we have Mach 1. So starting from case 3, from figure 13, increasing pressure gradient, we have Mach 1 inside the throat. All these curves 3, 4, 5, they go through same point in the throat, through Mach 1 in the throat. Practically, what does it mean? It means that in all cases, we have Mach 1, we have area which is constant, and since we have isentropic flow, we have also temperature same, right, equal to characteristic temperature, and pressure equal to characteristic pressure in the throat. Once we combine these parameters between, and we elaborate just one parameter which describes this process, we can use a definition of quantity of gas flowing through the nozzle, which is mass flow rate, m dot is equal to area multiplied by density and multiplied by velocity. Since we have area constant, we can use throat area, we can use density in the throat and velocity in the throat corresponding to our Mach 1. So since Mach 1 is same for all cases, it's equal 1, we have same density and same velocity for all cases. So independently, case 3, 4, and 5 will result for us in a constant quantity of mass which flows through the nozzle. And this is called choked flow. You can see on this figure right here, representing to us in coordinates of pressure difference or pressure gradient and mass flow rate. For all pressure gradients which would be significant enough to accelerate to Mach 1 in the throat, so all cases starting from this point and until the end, this blue line will be having Mach 1 in the throat. Okay, for all such cases, mass flow rate will be constant. It means ambient pressure will not influence on mass flow rate inside the nozzle. It means it's independent flow in the nozzle is independent from conditions outside of the nozzle, and the mass flow rate is constant for such pressure region. It's called choked flow. So practically, it's used in many applications. For example, inside combustion chambers, I will make a simple schematic. For example, this is a combustion chamber with a nozzle. Oh, not so nice. It's like Picasso. Okay, I will make probably just the part of this. Okay, combustion chamber, nozzle. Let's assume it's a part. And we have injector here, injecting fuel or oxidizer or mixture of fuel and oxidizer inside this combustion chamber to accelerate. It's not just related to combustion chamber, but for any process which use choked flow effect. For example, we are injecting this propellant with quite significant pressure ratio, okay, bigger than 0.5, or let's say, or reverse, okay. Our chamber pressure is at least 2 times smaller than injection pressure. It means that we can keep mass flow rate constant independently on pressure inside chamber. So you can choose any pressure inside chamber. You can change by changing relation between oxidizer and fuel, with relation on contraction ratio of the nozzle if it's a regulated or controlled nozzle. You can change by different ways pressure inside combustion chamber, but mass flow rate can be independent on this pressure inside chamber if you create conditions that feeding pressure is 2 times higher than chamber pressure. So this is very useful because you can separate flow in the injector from conditions of flow inside combustion chamber. So you can independently control these 2 parameters, and this gives for us a lot of advantages in organizing efficient propulsion. Another advantage is, since we have inside injector Mach equal 1, it means that any changes inside combustion chamber, for example, if we have pressure oscillations inside the chamber, here in this zone, pressure variation inside chamber, if we have Mach 1 inside the injector, these pressure oscillations will not go inside injection system, will not go inside the feeding system inside the tanks. So if we measure pressure in same time moment inside our injector, let me change, okay, we will see a constant pressure of feed inside the line. We will see a constant value. Even if oscillations happen inside chamber, they will not reflect on parameters inside feeding line, inside the tank, inside turbo pump, inside many elements of propulsion system. This is extremely important because oscillations inside chamber should not destroy all previous supply system of rocket motor. So, and not just applied to rocket motor. This is applied to many applications. For example, same for automotive industry, when you inject inside the combustion chamber of internal engine, etc., etc. Yes, it prevents propagation of instabilities from combustion chamber inside the tanks. According to question of Mauricio, I answered. It's not preventing instabilities by itself, but it prevents that these instabilities will cause some consequences inside the previous elements of feeding system and propulsion system. It's so-called gas dynamic separation of processes. Okay, creating Mach 1 in some region, we prevent that disturbances will go against flow, because disturbances always propagate with speed of sound. They cannot go with against velocity, which is having Mach 1 or supersonic. Propagations will always go together with flow, and we can limit the propagation of instabilities or oscillations or any other processes. For example, we can neglect change of ambient pressure when a rocket is flying higher, right? Chamber pressure stays constant independently if we test on the ground or we are flying already in the higher altitude in space. Okay. Flow structure inside nozzle will change for different altitudes, and outside external flow can also change for different altitudes. But since chamber pressure is more than 2 times higher than ambient pressure during motor operation, this ambient pressure will never influence on flow conditions and flow structure inside combustion chamber processes. I hope it's clear. There are a lot of applications of choked flow. These are just two applications, two examples I gave you. Main reason is, main process we have to remember is that choked flow creates Mach 1 inside the throat, which prevents that propagations of all disturbances after throat enter or cross this throat against flow. So propagations will not go against flow. This is giving a lot of advantages in organization of safe operation of aerospace structures. Okay, flow case when pressure gradient is not enough for continuous acceleration, results in a natural process of formation of normal shock wave, inside the nozzle. This normal shock wave may appear when pressure gradient is not sufficient. For example, here on figure 15, we can see that PE4 is not as small as it should be for all isentropic flow. PE4 is higher, so it means that the pressure ratio is not so big. And naturally, such flow results in existence of shock wave inside the nozzle. Such a shock wave can be of two types. Can be harder, like a normal shock wave, if pressure ratio is supporting existence of shock wave, of normal shock wave, or can be lighter version when the pressure ratio is closer to PE6, somewhere here, PE5 in the middle. It will result not in a normal shock wave, but it can result in formation of oblique shock wave looking like this. If you are simulating, you can find on your simulation such a flow structure that some oblique shock wave will be formed on the exit of your nozzle. Such a case is possible. You can see it by experimenting. You can see it by numerical simulation. And it's a natural way to have equilibrium of flow properties and thermodynamic properties. Nature takes care of everything. It creates or normal shock wave, or oblique shock wave, or isentropic flow, depending on pressure ratio. I have one video, at least one video, that explains how to calculate such flow analytically. Normal shock wave, oblique shock wave inside the nozzle. And you could see one example of calculation. I will not stop today. I do not see why I should repeat same information which we already have in questionnaires of gas dynamics. So if you are interested to know how to calculate presence or absence of normal or oblique shock wave analytically inside your nozzle, please see videos of questionnaires of gas dynamics in case of examples of calculation. It's one of the last videos of questionnaires of gas dynamics. Not the last one, but one of them. Okay, so I hope it's interesting, and Anderson also explains a lot how to calculate such a case, and I, in my video, show complete model how to find exactly this distance d, where a normal shock wave will be will appear. It's an iterative process. There is no direct calculation. It's an approximation. So we need several 3-4 iterations to calculate such position of normal shock wave. But it's possible to do analytically. We can determine position of normal shock wave inside nozzle. We can calculate flow distribution, analytical, similar to figure B and C on this screen here. And I showed in my video how to calculate some specific points of these curves. And if you are interested in the future, if you would like to understand more about this model, or you will need in your TCC or other projects to understand about this question analytically, I'm ready to answer and help you with such model. I know that this question is more advanced than just isentropic flow. It does not enter in calculation of work one. So for selected people, I'm ready to, for some people, I'm ready to explain, right? For people who need or interested to study. Anderson also does not show this model, so it's not an obligatory part, let's say. It's a very interesting part, but not for all. Case we can see here on figure 16 is intermediate case between PE5 and PE6, where pressure is creating to us gradient not exactly corresponding to isentropic flow, not exactly enough for isentropic flow. In this case, can create several types of flows depending on values of PE5 and PE6. Can be a case with a normal shock wave placed on the exit of the nozzle. This case is the most simple to calculate analytically. I think it can be done in just one or maximum two iterations of calculation. If you would like to calculate a nozzle where normal shock wave is placed on the exit of the nozzle, you need to couple model of isentropic flow inside whole nozzle and the model of normal shock wave theory on the exit of the nozzle, where you calculate pressure ratio which corresponds to normal shock wave relations. You remember probably that in normal shock wave theory, we have analytically defined pressure ratio as a function of Mach number. So depending on your Mach number on the exit of the nozzle, which is a function of area, you can calculate pressure ratio. And it will be also a function of area because Mach number is a function of area, which simplifies a lot. I gave this example in one of my videos, and Anderson is also explaining how to calculate such a case. If we have a bigger value of pressure 5, then pressure 5, which corresponds to normal shock wave, we can have oblique shock wave, which is shown here on case D. Oblique shock wave, which is placed or stays on the exit of supersonic nozzle. Okay. Then there are other cases where pressure is exactly equal to PE6, pressure exactly corresponding to isentropic flow, where exit pressure is equilibrated with this PE6. It creates for us uniform and uniform flow with no disturbances from atmosphere, because we have same pressure in the exit of nozzle and in the atmosphere. And in case where pressure of atmosphere is smaller than PE6, then this is case F, shown here. We have additional expansion of flow inside the atmosphere. In such case, instead of having shock waves, we have a set of expansion waves which expand our flow in external space. So flow inclines, flow expands, occupies more space. Such a case, such three cases, case D, E, and F, we can observe on the same rocket motor, on the same launcher when it starts from ground. For example, if you watch any launch of SpaceX, which are quite frequent nowadays, we can see the following picture, that on the launch pad, the flow jet is quite constrained. you can observe such a picture, which you can see on case D. Okay, quite constrained. You can even observe presence of shock waves on the exit of nozzle when the rocket launcher starts, if you look careful on the video. Then on some altitude, pressure equilibrates with the pressure of the nozzle. So we can have, we can see parallel absolutely flow to nozzle flow, case E, on some altitude. I think it's an altitude of 5 kilometers, more or less, or similar. I don't know exactly because they change pressure inside chamber. They regulate pressure inside chamber, so we cannot definitively say at which moment exactly this pressure will equilibrate, but at some point it definitely happens. So you can see parallel absolutely flow to atmosphere. And at high altitudes, you can see case F, where ambient pressure is very small. So we are exhausting to vacuum, and flow expands a lot. Even you can find on higher stages, for example, this rocket nozzle, and expansions happening to all directions like this. You can see a fan with a very high expansion angle from the nozzle. This is typical for high altitude flights. Okay, it means that flow on the exit of the nozzle is much higher than ambient pressure. Pressure in the nozzle is higher than ambient pressure, so it expands a lot. So all these three flows we can observe on many videos, and I think it's interesting next time you watch launch of SpaceX. I think it was planned for these recent days. Recently, they have launched a few days ago. And you can observe all these three types of flow on this launch, and it's extremely interesting because it goes absolutely according to a theory of gas dynamics. Okay, guys, I think we can stop this lecture at this point because it's all information you need to know to finish work 1. And on our next class, we can continue chapter 10, talking about diffusers, wind tunnels, and probably we can already start chapter 11. Let's see if we have enough time. Today, our class is shorter because I told you there are some things which are worrying a lot, and I cannot concentrate as much as I would like to give these lectures, but at least I could give you all information necessary to calculate work 1. So I expect delivery of work 1 according to schedule. Please do not forget we have a monitor, and she's expecting your questions about work 1, or if you need, we always can talk on our classes. Please send me in advance some messages or some questions you would like to discuss in class, and I will prepare for you answers which were not answered yet in a questionnaire of gas dynamics, and we could talk about these questions. Next Tuesday is a holiday, right? Carnival. So we probably have next lecture on Thursday. Do not forget, Thursday should be our next meeting. Thank you. See you next time.